welcome back to our series on Vertex Operator Algebras. Today we are taking a look at how Affinely algebras naturally sit in the formalism of formal series. This lecture is a steep crawl through some formalism, so to keep things as low stakes as possible, I've made a PDF of all the relevant formulae from today, and it's available in the show notes. Please download it if you like. Also, since most of the work today will be in reframing the known commutation relations in terms of formal series relations, I'll be leaving all the explicit proofs to you as an exercise, but I will give you a heads up on the few technical details that you might need. So let's start with a quick review of the basics of affine Lie algebras that we studied in Chapter 1. Given some Lie algebra G, equipped with an inner product, the extended affine Lie algebra Virgulia G involves the product of G with the Laurent polynomials over some formal variable t, centrally extended of course, with a central charge C and a degree derivation d. A generic commutator behaves as follows, with the central extension term becoming relevant when m plus n vanishes. Here the angled brackets refer to the inner product. Of course, d is the degree derivation on the Laurent polynomials, and the commutator of d with x furnishes the degree operator for the algebra. Let's now investigate how this structure maps to formal series. There is a natural product on the space of formal power series over a Lie algebra G into the formal series over G of two variables, one for each factor, furnished by the Lie bracket of G. Dealing with differently labeled formal variables is going to be a huge part of the mathematics going forward, and will be hopefully motivated by the physics to come. Suffice it to say, products of formal variables commute. To make contact with our previous constructions of affine Lie algebras, we basically look to make the gradings between these two constructions compatible. For the untwisted Virgulia G algebra, it's a z grading, an integer grading. For the involution twisted version, it's a integer plus 1/2 grading. In practice, this compatibility essentially works as you'd expect, perhaps though in reverse. You see, the coefficients of the negative nth power of the formal variable are essentially the nth grade elements of Virgulia G. This negative sign affords our traditionally positive, highest weight representations of Virgulia G to have a negative powers in the formal variables. In the context of physics, this amounts to poles in the correlation functions that define the observables in our theory. One way to think about this is that the affine Lie algebras are just neatly packaged by formal series, affording much more efficient calculations in what is to follow. Our first claim today represents a reformulation of the untwisted affine Lie algebra brackets in terms of formal series. For a generic element generated by x and y in some Lie algebra G, the relationship with formal series is more or less what you'd expect. Notice that here we've thrown in the formal delta functions to keep the algebra to a single formal variable, effectively. Note that in particular, the formal series degree operator big D acting on the delta function in the central term, and the associated minus sign. If anything, these delta functions make the algebraic structure more transparent than in that kind of physical operator product expansion approach. Note that the commutator of D with a generic element x is given by minus big D. Of course, it's important to keep in mind that these degree derivations are working on different formal variables. As will be the case for all of today's claims, we leave the proof to the viewer as an exercise, which in this case essentially amounts to taking derivatives of the delta functions and matching terms. We now consider the twisted case. Recall that the twisted affine Lie algebra is a subspace of Virgulia G that is invariant under the involution theta. Since G itself maps to so-called even and odd eigenspaces under theta, the space amounts to the direct sum of the even terms with integral powers of the formal variable t, and the odd terms with half-odd integral powers of t, and of course the usual central terms. For a bit of notation, let I be in Z2, that is either 0 or 1, so that given any generic element x of the algebra, we can write the projection xi So for a generic element in the formal series x of z, we have, where here x sub n implicitly means x sub n mod 2, aside from possible half powers, everything appears to be the same as in the untwisted case. The involution theta, of course, also acts on our formal series by essentially taking the limit that z to the 1/2 goes to minus z to the 1/2. Remember, these are formal variables, so we're being extra careful, i.e. formal, with our definitions here. With that, we can formulate our next claim to rewrite the Lie brackets of the twisted Affinely algebra as this mess, where now we have two sums over z2 and delta functions of half-integral powers of z. The degree derivations effectively work the same way, and so the rest of the algebra is of course familiar. Proving this result requires a bit of knowledge about the delta function of a fractional power. Here we see that delta of z is a symmetric combination of delta z to the 1/2 and delta of minus z to the 1/2. The combination z to the 1/2 delta of z is kind of like the antisymmetric version of that. One thing you might ponder at this point is how to adjust the result for an isometry that is not an involution, but perhaps say cubes to unity instead. FLM introduces another bit of useful notation involving the variables x plus or minus. This factor of 2 is merely a notational convenience to match up with the existing literature on the subject, probably. This can of course be extended to the full formal series, as you'd expect. The x plus terms are essentially independent of theta, but the x minus terms depend on whether you're in the twisted or untwisted sector. Where the sum in x minus is over the integers, in the untwisted case, it's in the integers plus 1/2 for the twisted case. Finally, we consider the Lie brackets of our new variables. Perhaps as expected, the brackets of even terms are the same regardless of twisting status. A mixed bracket of even with odd terms has, of course, no central term. Finally, the bracket of two odd terms is going to be very different depending upon whether we're considering the twisted or untwisted sector, as the twisted case now involves delta functions of half-integral powers of the argument. As advertised, this episode, like the corresponding sections in FLM, is kind of an unholy mess of formalism that isn't yet motivated. But this little section, this chapter 2, has essentially been a study of some formal techniques that will allow us to study the structure of vertex operator algebras with greater ease. So I'm posting a formula sheet so you can just print and pin it to the wall if you like. And you can simply refer to it as needed. Make sure to check out the show notes if that's of interest to you. And that's our show. Next time, we're going to start a little investigation into the related physics of conformal field theory and see how this ties in to formal series. Get psyched!